Welcome to the debate. Today we are diving into, well, a really monumental theoretical undertaking, the Nested Learning Framework, or NL. The source material kicks this all off by pointing out a critical, systemic failing in our current static large model architectures. They suffer from a sort of computational anterograde amnesia. They're limited to new knowledge in either immediate context windows, that's the short-term memory, or just their vast, long-past pre-training data. The models just don't have the right mechanisms for robust, long-term consolidation of new information.
Right. It's a foundational problem. The argument is essentially that current LLMs are inherently static because their learning algorithms are, frankly, too simple to handle continuous evolution and memory transfer across different timescales.
Exactly. And so nested learning tries to address this by fundamentally reconceptualizing machine learning models. It views them not just as, stacked layers, but as integrated systems of multi-level and nested optimization problems where each one is managing its own context flow.
This reframing is provocative, I'll give you that. But it leads us right to our core question for today. The debate really centers on where the primary value of this framework truly lies. Is the fundamental contribution of nested learning the theoretical rigor, the conceptual reinterpretation of existing parts like optimizers as these complex memory systems? Or is its value demonstrated almost overwhelmingly by the novel architectural and algorithmic innovations it makes possible, like deep optimizers and the HOPE model?
I'm going to argue that the conceptual framework and the foundational white box nature of NML are the primary, most valuable contributions here. The theory is what unlocks the entire design space.
And I will contend that no theory really stands on its own. The utility of this framework is fundamentally, and I think inextricably, linked to the superior architectural and algorithmic utility that we can see in the new designs it lets us build.
My position is really rooted in the unifying power of NL. The greatest contribution here is that it provides a mathematically rigorous foundation that unifies all these disparate elements of deep learning, attention, optimization, recurrence, under a single coherent concept: associative memory. NL reveals something that was, I think, previously opaque. The basic training process of even a simple one-layer, multi-layer perceptron using gradient descent is fundamentally a one-level associative memory. It's mapping data points to their required error signal, what the source calls the local surprise signal, or LSS.
And that translation of an optimization step into a memory storage operation is, I agree, a powerful idea.
And it extends so much further than simple gradient descent. Crucially, NAL shows that fundamental components like gradient-based optimizers, think stochastic gradient descent with momentum, they aren't just algorithmic hyperparameters we tune. They are themselves higher-level associative memory modules that are designed to compress and store their context flow, which is the history of past gradients. Momentum in this framework gets interpreted as a keyless associative memory. So it's storing information without explicitly tying it to a unique identifier or key. That alone is a profound intellectual insight, offering a kind of diagnostic view into the whole optimization landscape.
I acknowledge the elegance of that white box perspective. The transparency is definitely appealing. But does theoretical elegance actually translate to utility? I come at this from a different way. While that theoretical interpretation linking optimization to memory is vital, the true utility of NL is only realized when it gives us superior, measurable performance. And that demands moving past just reinterpretation and into novel construction. The framework's real importance lies in providing a new, high-dimensional design space, letting us create vastly more expressive learning algorithms than, standard GD or Atom.
But that engineering breakthrough is only possible because the framework gives us the blueprint to begin with.
I agree. The blueprint exists, but the house has to be built to prove its value. The core architectural contributions, the explicit development of deep optimizers, the inspiration for this self-modifying Titans approach, and, most importantly, the creation of the Continuum Memory System, or CMS, these are the tangible, empirical evidence of NL's success. The resulting architecture, HOPE, which leverages a self-referential sequence model with CMS, shows robust, state-of-the-art performance across very demanding tasks. This isn't just theory. We're talking lower perplexity, higher accuracy than established heavyweights like RetNet, DeltaNet, and even the original Titan's architecture. That superior performance validates the paradigm, not the other way around.
Okay, let's ground this debate by diving into the optimizers themselves, since they're the first level of nesting. I maintain that the theoretical breakthrough is the insight itself, decomposing gradient descent with momentum into a two-level optimization process. The fact that the inner level, the momentum term M, is explicitly an associative memory storing gradients, that clarifies the function of existing methods and directly connects them to classical concepts like fast-weight programs or FWPs.
I'm sorry, but I just don't buy that the decomposition itself, while it is clear, is the primary contribution. Decomposition is just describing what the existing momentum term is doing. The power of the NL framework is that it's prescriptive. It suggests how to fundamentally extend this functionality. Standard momentum, as a keyless, linear memory, has extremely limited expressivity. I mean, if it's just a linear filter on past gradients, its ability to model complex dependencies is minimal.
And the theory explicitly diagnoses that linearity as the bottleneck.
Precisely, but NL's value is manifest when it enables the design of deep optimizers. Take deep momentum gradient descent, or DMGD. This is where we replace that linear memory layer for momentum with a more powerful multi-layer perceptron. This isn't just a small tweak, this transforms the optimization process. By substituting a complex nonlinear MLP for simple linear filtering, the model gains the ability to effectively learn its own context-dependent optimization strategy. The model is literally optimizing how it optimizes.
That's an interesting point. But I'd argue that even the design of DMGD required the conceptual clarity that came before it. How do you justify replacing the linear layer unless you first rigorously define the momentum term as an associative memory component that is itself bottlenecked by its linearity? You need that conceptual framework to even motivate the replacement.
The true test of the framework's utility, though, is when it suggests fundamentally new optimization objectives. NL lets us define optimizer objectives based on the delta rule, like the L2 regression loss. This replaces the standard, simple gradient objective with one that explicitly tries to train the memory module, the M, to optimally predict the required learning pattern. This fundamentally increases the capacity and effectiveness of the learning algorithm itself. The conceptual unification is foundational, yes, but the deepening of the optimizer into an expressive, self-learning component is where the practical impact is felt and where performance gains really start.
Let's shift levels now, because the ability to design something like DMGD only exists because the conceptual framework first established a structural hierarchy. Consider our second contention. The formal definition of the hierarchy based on update frequency is absolutely essential. This is the guiding principle that lets us sort model components into these ordered levels. Higher levels naturally have lower frequency updates. For example, the global model parameters update far less often than the fast-changing short-term memory components like momentum.
I agree that the frequency concept is crucial. It's what links memory timescale to stability. However, defining levels purely by frequency is, well, it's an abstract notion. It only becomes truly meaningful when you instantiate it in a physical system, the Continuum Memory System, or CMS. I would argue the map only becomes relevant once you start building roads.
But the CMS is the result of the map.
And the result is the measurable utility. CMS formalizes this multi-timescale concept as a chain of specialized MLP blocks. In this system, the parameters for each level are explicitly designed to update only every C steps, and C is the consolidation period for that memory level. This structured approach provides a frequency-defined knowledge storage for each level, mimicking the slow consolidation processes we see in biological memory.
And we have to emphasize here that NL reveals the conventional transformer block itself is just a special, very limited instance of the CMS formulation where the consolidation period is instantaneous. The memory depth K is set to 1.
Exactly. And the practical utility lies in moving beyond that K equals 1 limitation to manage context and memory consolidation over multiple, long timescales. This directly addresses the core issue of LLMs being static and suffering from this anterograde amnesia. The CMS architecture is not just an elegant theory. It is the crucial realization of the frequency concept into a working system that can dynamically transfer knowledge from fast, immediate memory to slow, consolidated memory. The system has to be built to prove the theory.
That's a compelling argument for architectural realization, but let's just step back and consider the neuroscientific analogy that motivated this entire endeavor. The starting point, the analogy of current LLM suffering from anterograde amnesia, that's what validated the NL approach in the first place. This analogy correctly identifies the need for online consolidation, which is analogous to rapid synaptic consolidation in the brain, as the essential mechanism for transferring new information from short-term memory, like an attention layer, to long-term memory, like the feed-forward layers. This theoretical guidance, the very problem definition, is the critical intellectual anchor provided solely by NL.
The intellectual inspiration is definitely appreciated, but empirical performance is the ultimate validator of the engineering principles derived from any analogy. Simply identifying the problem isn't enough. Solving it with a superior system is the breakthrough. Hope, which leverages these NL insights, achieves state-of-the-art results because it becomes a self-referential learning module. It refines its own update algorithms based on context, drawing inspiration from that self-modifying Titans architecture.
And what specifically does Hope do that validates the framework?
Well, the data shows Hope outperforms RetNet and DeltaNet, and it often surpasses the original Titans. Why does that matter? Because RetNet and DeltaNet are strong competitors in the recurrent sequence modeling space, and Titans introduced this concept of self-referential attention. Outperforming them suggests that dynamically changing the key, value, and query projections based on context, the self-referential part, when combined with the deep, multi-timescale memory module of CMS, is the required engineering breakthrough. The performance gains prove that structuring the model as nested associative memories actually works to integrate new information faster and more effectively than its competitors. That utility is the true contribution.
I'm still unconvinced because you're focusing only on the end product without appreciating the foundational structure that made that product viable in the first place. We come back to the white box nature. The structure begins with the fundamental interpretation of memory acquisition. The theoretical move is interpreting training backpropagation as solving a specialized optimization problem, acquiring effective memory that maps data samples to their necessary local surprise signal. This precise formulation reveals the inherent memory function in standard gradient descent. It turns a heuristic process into a transparent, mathematically defined one.
That standard formulation, however, while it's descriptive of single sample updates, it fundamentally ignores dependencies between data samples. And in sequential modeling, which is the main application here, token dependencies are everything. Tokens are not independent data points, so the standard objective doesn't optimally handle sequence history or context dynamics. If NL is just a descriptive tool, it's failing to address a key computational challenge.
But the theory doesn't stop there. It allows us to derive a better objective.
Correct. NL's application must extend the objective to solve this limitation, and that extension is the practical benefit. Instead of the simple standard objective, the framework suggests using an L2 regression objective. This is a major shift. This objective isn't just solving for the gradient, it is solving for a weight matrix W that optimally regresses the input onto the required gradient. By using regression to train the internal memory components, we are forcing the memory system to better handle the statistical dependencies inherent in the data sequence.
And it is the framework's capacity to derive that sophisticated regression objective from first principles of nested memory systems that I find most valuable. It's not some empirical hack, it's a mathematically justified necessity that is driven by the theory.
It is the fact that Hope and Deep optimizers actually use this algorithmic adjustment derived from the NL perspective that makes the framework generative and useful. This algorithmic adjustment is the practical benefit that moves the framework from a descriptive tool to a mechanism for measurable improvement, allowing the architecture to achieve those superior performance metrics we discussed. The theory guides us, sure, but the practical, measurable algorithmic improvements are the true reward.
So we've explored the tension between the conceptual clarity offered by nested learning and the powerful, performant architectures it enables. I still stand by the view that the strength of NL lies in its ability to transparently and mathematically represent complex deep learning systems, optimizers, recurrent layers, all of it, as a coherent, unified system of nested associative memories. This provides the essential, unified, white box vocabulary necessary for any sophisticated architectural advancement. Without this conceptual map, the architectural successes would lack theoretical robustness. They'd seem more like empirical tweaks than justified design choices.
And I reiterate my position that a powerful theoretical framework has to, at the end of the day, yield demonstrable superior engineering outcomes. The ability to use NL to design expressive components, like deep optimizers, and the performant CMS-HPE architecture, which tangibly overcome the static, amnesiac nature of traditional LLMs and show concrete gains in perplexity and reasoning accuracy, that constitutes the essential contribution. The theory is indispensable as a starting point, but its value is proven through the practical utility it unlocks in solving the critical problem of continual learning.
It is absolutely clear that within the nested learning framework, the understanding of optimization and memory consolidation are deeply and fascinatingly interwoven concepts. They really are two sides of the same coin.
Indeed. NL provides a crucial lens for understanding modern AI systems, regardless of whether one prioritizes the conceptual transparency it offers or the superior performance of the novel architectures it facilitates. The exploration of this interplay between nested optimization and hierarchical memory structures remains complex and deeply important, which suggests there is much more to uncover in the material.